Okay, so this is lecture 16, where we're finally going to start talking about cardinality. Cardinality for finite sets is just a number of elements in the set, and it's not that exciting, though we'll do something that's quite fun called the Inclusion-Exclusion Principle. It gets much more interesting when we start to look at cardinality for infinite sets, when we start to see that there's different kinds of infinity. So I'll say more about that in a bit. Now, one new handout, which most of you have got, I think. There's a few spares of the previous handouts. Those are in the box on the chair next to the desk. And the coursework for handing in, that should be alphabetical by surname. Some people put their work in the wrong tray last time, which makes it slightly harder for us to organise it into the folders for returning. So it'd be easier if everybody put them in the right tray. But as long as most of you do it, it'll be all right. Okay. So now we're ready to talk about finite sets and infinite sets. Now, actually, there are one or two issues here which we're not going to go into in the greatest of depth because the foundations of mathematics have got some tricky bits at them. I'm going to take it for granted that we know and can recognise a finite set of objects when we see one, and that we know what a number is. But that's actually taking quite a lot for granted, but you have to stop somewhere. Right, so we're going to say a set is a finite set if it's either empty, in which case it's got no elements, the number of elements will be naught, or it's got exactly n elements for some positive integer n. Okay? So it's a set where you can count the elements in such a way that the result is a finite number, a natural number, or 0 because it's empty. Otherwise, it's an infinite set. So that's one where there's infinitely many elements. And then we'll use this modulus notation for the cardinality of a finite set. It can cause confusion, but that's how we'll denote it. It's quite a standard way of doing it. Right, so this works for finite sets. What you do for infinite sets, we'll see later. Okay. And as I said, the empty set has got no elements in, so we say it's got the cardinality of it is naught. Otherwise, the finite sets will have exactly n elements, where n is either naught or some natural number, and then we'll call it an n set. So this is just boring terminology, but it does save a bit of time sometimes. Here's a set with exactly 4 elements in it, 4 different elements, of course. If I wrote down the same elements more than once, that wouldn't mean it's got more elements in. You have to see how many different elements it's got. So that's a finite set with cardinality 4, and that makes it a 4 set. And then sometimes we'll talk about k subsets of a set, which is a subset with k elements. So here I take this set S, and then if you just take 1 and 4 out of it and put that in a subset, that gives you, that's a 2 set, but it's also a 2 subset of the original set. And you can have a 1 subset. I tend to call 1 subsets, I often call them single point sets, but 1 sets are single point sets. Okay, that's just terminology. That's on your notation sheet as well, I think. Now, you shouldn't get confused between finite sets and bounded sets, or try not to get confused between finite sets and bounded sets. You see, this interval, closed interval 0, 1, is a non-degenerate interval in the real line. It's obviously thoroughly bounded. Everything is between 0 and 1. But there's infinitely many elements in there. In fact, we're going to see later, there's uncountably many elements in there. It's a very big set, really, by comparison with the natural numbers. So all of these sets here are infinite sets. Of the ones mentioned here, this, the closed interval 0, 1 and R are the biggest infinities, and N, Z, and Q turn out to have the same rather smaller infinity called countable infinity. But they're not finite, they're still infinite sets. Okay. So we'll look at those cardinalities later, and you might have a look at my Hilbert's Hotel video. I remember I set a question in the exam 2 years ago where those people who had had a look at this video probably had an advantage. So you might find that sometimes, well, it's a usual thing. It's the more you know and understand, the better your chances of being able to answer an unseen part of a question quickly. Right, so there's a link on Moodle. Right, okay, now I want to talk about bijections between finite sets, because finite sets are easier to deal with than infinite sets, and some rather special things happen. Now, I'm not going to get you to vote on this, I'm just going to tell you what's going on. But you might want to think about this. What's the difference between an infinite set and a finite set? Well, some funny things happen, right? Here A has only got 5 elements. And I'm going to look at maps from A to A. Now, suppose I take a function from A to A, and it's injective, so that everything has to go to a different place. So I could send 2 to 3, and I could send 3 to 8, and I could send 8 to 6. But I'm not allowed any repeats, if I want an injective one. Then I have to use them all up, because the 5 elements are being sent to 5 different places, and there's only room for 5 things. So I have to use everything. The result, the interesting thing is that if you start being injective, it forces you to be surjective too, if I'm going from a finite set to itself. I can't miss anything out. If I did say, I'm going to try and miss out 12, then I'd be trying to send all 5 elements to the other 4. And the Pigeonhole Principle says you can't do that. You can't put 5 letters into 4 pigeonholes without putting at least 2 in one of the pigeonholes. So you can't do it. So if I take an injection from this finite set to itself, it has to be a surjection. But the same goes the other way around. If you take a surjection from this set to itself, you better not repeat any. If you want to manage to map these 5 elements onto all 5 of the elements, you better not have any repeats, because say I send 2 of them, say I send 2 and 3 both to the same thing, say I send 2 and 3 both to 2, then I've only got 3 elements left to try and cover the remaining 4, and you can't do it, right? So if you're trying to be surjective from a finite set to itself, then you can't afford any repeats, and so you have to be injective as well. The result is that if you take a map from a finite set to itself, then it's an injection if and only if it's a surjection, if and only if it's a bijection, which makes life very easy when you're mapping a finite set to itself. It's not the same. If you're mapping a finite set to a different finite set, you get different answers. We'll talk about that a bit later as well. But now let's think about a map from the natural numbers to itself. Well, here's a nice injection for the natural numbers to itself. I thought I'd change that colour. Let's go back to a less purple colour. All right. So this is no. For example, if you do f of n equals n plus 1, then actually rather similar to something that came up in the first class test, if you take a positive integer and add 1, it's still a positive integer. But, and of course this is injective, because if m plus 1 equals m plus 1, then m equals n. So that tells you that if f of m equals f of n, then m has to equal n. So that makes it injective. Not surjective because, again, as in the class test, you can't find a positive integer which you can add 1 to and get 1. So f is not surjective. And what f actually does is you start with 1, 2, 3, 4, and so on. And it goes to 2, 3, 4, 5, and so on. You don't get to 1, okay? what this tells you, in fact, in terms of cardinality of infinite sets, is there's just as many of the bottom row as there are in the top row, as far as cardinality is concerned, even though there's one number missing. It's still the same kind of infinity. There's this actually does give a bijection from F to its image, but not, it's a bijection from N to the set 2, 3, 4, and so on, which is quite interesting. Because if you've got a bijection between two sets, then basically that means they've got the same number of elements, even if they're infinite sets. They've got the same cardinality, as we'll see when we talk about cardinality of infinite sets. Same cardinality, but one fewer elements in some sense, because we threw one element out. Right, okay, and the other one is false as well. And I'll leave that to you as an exercise. Find a surjection from the natural numbers to natural numbers that's not a bijection. That means it must have at least one repeat. So I'll leave that one for you to think about. But by the time we've looked at some other examples, you should have a pretty good idea how to make a surjection from the natural numbers to natural numbers with some repeats in. Okay. Any questions about this so far? Because we're concentrating on finite sets today, but I want you to see that finite sets and infinite sets are different. So, everybody happy so far? Well, okay. I'll take that as a yes. So, we're going to assume the following elementary facts, which we won't prove. How would you prove them? You can prove a lot of these facts by induction, in fact, on cardinalities of various things. So if you want to do them really properly, you could do them by induction. You can quote the Pigeonhole Principle sometimes to help you, which is something else you could prove by induction. Eventually, you come back to what is a number, which is a terrible problem. Okay, right, so I'll just stick to non-empty sets to avoid any problems. At this time, X and Y may be different finite sets, okay? But they're going to be non-empty, but they don't have to be the same set as each other anymore. Then you get slightly different results. But bear in mind what happened when X and Y were the same set, then they had the same cardinality and same number of elements, and so you got some of these things for free. So when can you find an injection from a set X into a set Y? They're finite sets with, they're non-empty finite sets, and you're looking for a function from X to Y with no repeats. Well, basically, the Pigeonhole Principle says you can't do this unless Y's got enough elements in. So you can't do it unless the cardinality of Y is at least as big as the cardinality of X. On the other hand, if the cardinality of Y is big enough to fit X into, then there's always a way to do it. And all you have to do is write the elements of X and Y out in some particular order, who cares, and send, once you've chosen an order for the elements, you order them however you like, and then you send the first element of X to the first element of Y, and the second element of X to the second element of Y, and so on. Now, they might not be real numbers, you might not be able to order them in the usual way, but you can still do something like that. And as long as the cardinality of Y is big enough, you'll run out of elements of X before you run out of, well, no later than you run out of elements of Y. The same the other way around, a surjection from X to Y, this time you're allowed repeats, but you have to get to everything in Y from at least one thing in X. You can't do that unless you've got enough things in X. Otherwise, you will run out of elements of X before you can cover everything in Y. But as long as there's enough things in X to cover Y, you can do it. So, of course, that doesn't say that every function is an injection between these sets. It just means it's just a question of whether you can find one. You can find an injection if and only if the cardinality of Y is big enough. You can find a surjection if and only if the cardinality of Y is small enough, or cardinality of X is big enough. And of course, if you can find a bijection between finite sets, which is one of those ones where you can get to everything in Y from exactly one element of X, you can only do that if they've got the same number of elements as each other. Okay. And same sort of argument as before. You write the elements out in some order or other, and then you see what happens. Right. And then, very like what we just said before, when you're mapping a set to itself, and essentially for the same reason, if the two finite sets have got the same cardinality, then every injection is a bijection, every surjection is a bijection. So every injection is a surjection, and every surjection is an injection. As long as the sets have got the same number of elements, and that number is finite, then the three kinds of function coincide, which is handy if you can't remember which one's which. But you do need to remember which one is which, especially since in the exam I ask you almost every year what an injection, what a surjection, and a bijection is. I don't promise to ask you every year, but certainly a bit of a habit of mine to ask you what injections, surjections, and bijections are. So there's a good chance that comes up, or something similar. Anyway, right. So there you are. Every injection from a finite set to itself is a bijection. Every surjection from a finite set to itself is a bijection. But remember, this only makes sense if they're finite sets. Some of it works if you allow the empty set, and some of it doesn't. For example, there aren't any functions from a non-empty set to the empty set, which is a nuisance. So that means there's no surjection either. There are injections from the empty set to other sets, because you can use something called the empty function. But unfortunately, there's no function from a set to the empty set. So that's a slight annoyance, and that's why I said let's stick to non-empty, because of the stupid things that happen with the empty set. Okay. Right, now, again, something that we're going to regard as obvious, but which you can prove by induction if you want to, or you can prove it from some of the other things that we will prove later. Suppose you take sets which are disjoint. So x and y disjoint means that the intersection is empty, and they've got finitely many elements in. Then you can say how many elements there are in the union. It does just involve adding the cardinalities. So here you've got x with a few things in, and you've got y with a few more things in. But they don't share any elements. Then you can see here x has got 4 elements and y has got 3 elements. And when you take the union, because there wasn't any overlap, you really do end up with 7 elements and not any fewer. Whereas if you did have some overlap, you can guarantee you'd have fewer than 7. Because the overlap will, if they did share any elements, then when you added the cardinality of x to the cardinality of y, you'd be counting some of the elements twice, which is where the inclusion-exclusion principle comes in, we're going to see. And of course, now you can do the same thing if you've got finitely many sets. This is a finite number of finite sets. Each of the sets is finite. And their pairwise disjoint means that no pair of them share any elements. People generally say pairwise disjoint. There's another notion of disjoint you could use for sets, which I don't want to get into, where you say that the intersection of them all is empty or something like that. Pairwise disjoint is safer. It means that every pair of them is disjoint, but it still means none of them share any elements with any of the others. And then you just do the same picture here, except you've got a few more sets, and then you want to count the elements, well, you just add up the numbers again, and that's what this says, that if you've got sets that don't overlap, and you know how many elements there are in each, then the number of elements in the union is the sum of the elements in the numbers. And in fact, you can use the 2-set version to prove the m-set version by induction on m quite easily. But how you prove the 2-set version is probably by induction on various things, and we won't go there. We'll just say that that's blatantly obvious for us, and we'll stick with it. Okay. So here's a question for you to think about. It'll be easier after we've done some more theory, but you can probably work it out anyway. A is a 15 subset of Z. That means A is a set of integers, and it's got 15 different elements in it. So a 15 subset is something with 15 elements in, right? So A is a 15 subset of Z, and I tell you the following. 7 of the elements of A are even, 9 of the elements of A are multiples of 3, and 2 of the elements of A are neither even nor multiples of 3, and I want you to tell me how many elements are multiples of 6, and I'm going to let you work this out for yourself, okay? I'll give you a couple of minutes to work this out, and then we'll see what you come up with. I've zeroed the votes, so you can vote whenever you like, as soon as you've worked it out. And I'll pause the recording then. Okay, 40 answers with a big majority in favour of C, with a few other answers scattered around. So the answer is indeed 3. Congratulations. Now, if you know the inclusion-exclusion principle, you can use it pretty much straight away, but I'll do it the slow way. I've drawn a Venn diagram. Here's A, which we know has got 15 elements, okay? And the question is, where are those elements? I've got here a set of even elements of A and a set of multiples of 3. The X represent those things which are even but not multiples of 3. The Z are those things which are multiples of 3 but not even. And the Y, that's the ones which are even and multiples of 3, which is the same as the multiples of 6. So it's Y we're trying to find out. So you can write down some equations. We need to determine Y, okay? We have 2 plus X plus Y plus Z is the number of elements in A, which is 15. And you've got X plus Y. X plus Y is the number of even elements, which was 7. And Y plus Z is the number of multiples of 3, which is 9. And you can solve those 3 equations to find that Y is 3. In various different ways. So the final numbers you end up with, when you've worked it out, you get 3 here, what is it? X plus Y was 7, so there must be 4 here, and Y plus Z is 9, so there must be 6 here, and that gives you how many elements in A? 6, 9, 13, 15, so that's satisfactory. But how you get to that 3 the quick way is, it turns out what you should do is, well, A has 15, so the union here has 13, as we can see, that's right, 6, 9, 13. But if you added those 2 numbers together, 7 and 9, you get 16, which is 3 more than 13. And that's where the 3 comes from. And that comes from the inclusion-exclusion principle that we're going to have in a minute. So that fits with the following thing, that the number of elements in the union of 2 sets is obtained by adding the number of elements in each of the sets and then subtracting the number of elements in the intersection. The reason for that is that, as I mentioned before, when you add the number of elements in A to the number of elements in B, you count 2 for each of the elements in the intersection, when you should be counting 1. So you have to subtract that off again. It starts to get less obvious when you go to 3 sets. When you go to 3 sets, you want to know how many elements are there in the union of these 3 sets, A, B, and C. Well, you start by adding how many elements in A to the number of elements in B to the number of elements in C. But then you counted the things in the intersection of A and B twice, so you better take it off. You also counted the things in the intersection of A and C twice, so you better take it off. And you counted the things in the intersection of B and C twice, so you better take it off. But then you've taken off too many of the A intersection B intersection C's, it turns out, so you have to throw one back in. Now, if you go to more sets, it works exactly like this. You add the numbers in each set, then you subtract off those things which are in intersections of 2. But then you have to add in all those things, the numbers, for all the different intersections of 3, but then you have to subtract off all the different numbers you get for intersections of 4, add on all the different things you get for intersections of 5, and so on. And it always works, no matter how many sets you've got. And I think it's not obvious that that's exactly what you do. It's okay, it's easy enough for 2, it's not too bad for 3, but the more sets you've got, the less obvious it is that how many times exactly you've overcounted, undercounted things, and that it works. But we're going to prove it in the workshop. Well, pretty much prove it anyway. I'll give you a very silly argument using characteristic functions. I don't really think it's the right argument at all, but it does, however, prove it, and it does give you a bit of practice in seeing how cardinalities of the sets relate to their characteristic functions. And it works in probability by the same argument too. But you can also look at Wikipedia, which is always interesting. So I think I won't say more here. I'll move on to something completely different. Binomial coefficients and the binomial theorem. Have you already done this in ACF? I can't remember what order things are done in. Have you done the binomial theorem in ACF? You haven't. Okay. So recall may be, so this recall may be the first time you see it then. In which case, when you do it in ACF, you'll be reminded of what you see here. In ACF, however, you will actually prove the binomial theorem, I think, by induction. It's a bit ugly, but it works. Okay, so first of all, what are the factorials, and what on earth are we going to set naught factorial to be? Naught factorial is a convention that we take that to be 1. Naught factorial and 1 factorial are both taken to be 1. 2 factorial is 2 times 1, that's 2. So then we get 6, 24, 120. You multiply all the numbers so far. So 5 factorial is 120, 6 factorial is 720, etc. They grow rather fast, a lot faster than, say, after a while they grow much faster than something like 1,000,000 to the power n. So it does take a while to get there, but once you get past 1,000,000, n factorial starts growing faster than 1,000,000 to the power n. Up until that point, 1,000,000 to the n is rather large compared to n factorial. And I recall from Analytical and Computational Foundations, or possibly tell you for the first time, what the binomial coefficients n choose k are. This is pronounced n choose k, and I'll tell you what the binomial theorem says. Okay, so n and k are non-negative integers, and k is less than equal to n, and n choose k is n factorial divided by k factorial times n minus k bracket factorial. That's the factorial of n minus k. So, for example, 6 choose 2 is equal to 6 factorial over 2 factorial times 4 factorial. And 6 factorial over 4 factorial, everything cancels except the 6 times 5. So that's 6 times 5 divided by 2 factorial, which is 30 over 2, which is 15. And so on. So that's how you work them all out. It's convenient that you can cancel most of the big factorial using the bigger number underneath, which gets rid of the first few, so that you don't have to multiply too many big numbers together. And more generally, so n choose k, again, same reasoning. You can, it's n times n minus 1 and so on down to times n minus k plus 1 divided by k factorial, which is similar to what we did here. Okay, that's because you cancel out, that's cancelling out the terms up to n minus k. You can use product notation. means you can product from 1 to k n plus 1 minus j over j. That's quite a useful way of doing it. So that's n over 1 times n minus 1 over 2 times n minus, if I do this right. Have I got this right? Let's have a look. N minus 1 over 2, n minus 2 of 3 times n minus k plus 1 over k. So that makes it easy to work out things like n choose 3. This works only for n greater than 3. N choose 3. So n choose 3 is equal to n times n minus 1 times n minus 2 over 1 times 2 times 3. Which you can, no, you could put 6 on the bottom if you like. Okay. That was quite useful a couple of years back in the exam paper. Right. So what does the binomial theorem say? Oh, by the way, these are always integers in this setting where n and k are non-negative integers and k is equal to n. These always turn out to be integers, which is not obvious, but works. And one of the reasons it turned out to be integers is because you can get them using Pascal's triangle. Pascal's triangle is full of integers. If you ever see Pascal's triangle, 1, 1, 1, 1, 2, 1. One, 3, 3, 1, and so on. 1, 4, 6, 4, 1. You can read off 2, choose k along here. You can read off 3, choose k along here. You can read off 4, choose k along here. And so on. And in fact, if you write Pascal's triangle is quite a useful way of remembering what the binomial coefficients actually are, if you don't want to do it the other way. But another reason why they're always integers is because it turns out that the number of k subsets of an n set is n choose k. Another thing you can prove. If you want to know how many different ways are there of choosing k objects out of your pile of n, you get n choose k, which is probably why it's called n choose k, because you have to choose k from the n. And was proven or will be proven by induction in ACF, the binomial theorem. Here's a nice way to work out what a plus b to the power n is. So this comes out as a to the n plus n times a to the n minus 1b plus n minus 1 over 2 times a to the n minus 2 times b. By the time you get to the n, you actually get back to where you started. They start, n choose k is the same as n choose n minus k. So the last two things finish up like plus n times a b to the n minus 1 plus b to the n. You'll find there's a symmetry around the middle in the binomial coefficients. So it's quite useful. But in particular, I may have meant, yes?
Is that meant to be a b squared in the third?
Oh, yes, please. Thank you. Yes, absolutely. Thank you for that. So in particular, a few years back, I asked the second years to cube something. It was a cube of a plus z or something. I can't remember what it was. And they all multiplied out the three brackets and got random results because there's so many ways to get it wrong. So please, if that happens to you, don't do that. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. by the binomial formula straight away. So don't forget the binomial formula. It could save you a lot of time and stop you making mistakes. Okay. So I'm not proving the binomial formula. We'll take it as read. But I do want to show you a nice thing, a couple of nice things you can do with it. Okay, yeah. So here's what I said about n choose k. If x is an n set, then n choose k is exactly the number of k subsets of x. So, as it says, there are various different ways to prove it. One is to look at 1 plus x times 1 plus x, and so on, times 1 plus x with n brackets, and ask, how do you get x to the k out of that? Well, to get x to the k out of that, you get it by using the 1 from n minus k of the brackets and using the x from k of the brackets. But there's lots of different ways you can choose it. So you get 1 for every different choice of k brackets you have. So there are n choose k different terms. So so if you multiply it all out, there are 2 to the n terms. Each of which is obtained by choosing 1 or x from each bracket. Now, of those terms, if you want to get x to the k, you must have chosen k of these brackets we're going to take x from, but you get 1 term for each choice of k. So for every k subset, so for each choice of k brackets, for each way of choosing k brackets from these n, you get 1 towards your coefficient of x to the k. And that's why you get n choose k. So there are n choose k ways to choose k of the n brackets to use x rather than 1. You use x from k of them, you use 1 from the rest, multiply those up, and you get x to the k. But there's n choose k ways of doing it. So the binomial theorem, okay, you can either you can do it either way round. You can use the binomial theorem to prove that there are n choose k sets, or if you manage to prove there are n choose k sets, you can use that to prove the binomial theorem. Either way, but I won't actually prove either in full. But here's a nice thing you get by looking at 1 plus 1 to the n. And you can also do this by thinking of the number of subsets of an n set. So if you've got a set with n elements, how many subsets of that set are there with no elements? Well, just the empty set, so there's 1. How many subsets of this set have got n elements? Just 1. That's n choose n. N choose n is 1 because you don't have any choice. You've got to choose all the elements. And n choose 0 is 1 because you don't have any choice. You have to choose none of the elements. But the other ones are different. Now, the number of subsets of your n set in total is 2 to the n. That's how many subsets an n set has got. Each element is either in or out. So if you add up over all the k, the number of k subsets, you get the number of all possible subsets, which is going to give you 2 to the n. On the other hand, you can do it by the binomial theorem instead, because 2 to the n is equal to 1 plus 1 to the power n, which is equal to the sum, by the binomial theorem, sum from k equals 0 to n of n choose k, first thing to the k, second thing to the n minus k. This doesn't have much effect, though. 1 to the k times 1 to the n minus k is still 1. So that's where that one comes from. And there's a related very nice formula which tells you what the sum from k equals 0 to n of n choose k times minus 1 to the k is. Does anybody know what you get if you take the sum from k equals 0 to n of n choose k times minus 1 to the k? Have you got it? It is 0. Do you know why?
Well, it's symmetric around the axis. So if you take 1 plus minus 1 to the power n, you get 0 to the n, which is the same as sum between n and k.
That's right. So your symmetric about the axis is a good one, except when n is even, when you get this funny term in the middle. It's a slight nuisance. When n is even, when n is odd, you get an even number of terms and they all cancel. When n is even, you get an odd number of terms, and the term in the middle that isn't cancelled by anything. And so you have to use the other argument, which you gave as well. So we'll use the 1 minus 1 argument, okay? Because it's equal to 1 minus 1 to the power n. I'll rewrite that as, you see, 1 minus 1 to the power n, you can think of that as minus 1 plus 1 to the power n is equal to, by the binomial theorem, this is naught, of course. And now we do it with the binomial theorem, and you get the sum from k equals 0 to n of n choose k times minus 1 to the k times 1 to the n minus k. The 1 to the n minus k still doesn't do anything. That was useful in last year's exam. So you can do quite clever things with binomial theorem. And wait a minute, I can't remember. I think this one did come up in last year's exam. That's right. And something similar came up in last year's exam with a 2 and a minus 3 or something like that. You can do a lot of funny tricks with the binomial theorem. Okay. Right. Any questions about factorials, binomial coefficients, the binomial theorem? If not, then I'll give you a break till 4 o'clock, and that will give you a chance to hand in your coursework to the 4 trays. Try and put them in the correct one, alphabetical order by surname. Well, alphabetical trays by surname anyway.